In this short video, I'm going to talk about viscosity. Viscosity is a measure of a fluid's resistance to motion. And that motion is because of attractive forces of fluid's molecules. Consider this. You have a cup of water and a cup of honey. Which one is easier to pour out? I'm pretty sure that you agree with me that water flows easier, right? And that's because honey is more viscous than water. There is more resistance to flow in honey than water, right? So viscosity of honey is higher than viscosity of water. Now let's go over how we can describe viscosity in fluid mechanics and how we can have a mathematical representation for that. Let's do a thought experiment. In our thought experiment, we have two surfaces. The bottom surface is stationary, it's not moving, and the top surface is a plate. And in between these two surfaces, we have a fluid. Let's say we have some type of oil. We want to find out what would be the velocity of oil in between these two surfaces. Just to help you to understand a little bit better what I'm talking about, I'm going to sketch it over here. So we have, this is the bottom surface, and it's not moving. And this is the top surface, which is a plate that is moving with the velocity of capital U to the right-hand side. And in between these two, I have a thin layer of oil. All right, directions, this would be X and this would be Y. Okay, so what I'm gonna show you right now, I'm gonna give you the velocity of oil at every Y points in this direction. So Y increases from over here, and I'm gonna go over here point by point and tell you what would be the velocity of oil. Let's start from this point over here, which is right below the surface. Right below the surface, the oil is moving as fast as this top plate. So velocity over here is going to be capital U. A little bit lower than that at this point, the velocity is going to be decreased, right? Why? Because of viscosity, internal friction. So viscosity over here is going to be something like this, a little bit less than that. Velocity over here is going to be smaller. The velocity is going to decrease all the way. And now I'm going to talk about this point, which is just a little bit above the bottom surface. Right at that point, because those molecules and those particles of your fluid are kind of stuck to this stationary, to this fixed plate, they're not moving. So velocity on this fixed plate is equal to 0. And this condition is called no slip condition. Also, it's called no slip boundary condition. All right, so I'm going to show you the velocity distribution like this. Perfect. And then show you all the vectors over here. And these vectors show you the magnitude of velocity at each y that we are considering. Okay, now that we have this, we want to talk about viscosity. We want to measure viscosity and see what is the relationship of viscosity with this. I am going to tell you that we can measure the velocity gradient at any point over here. The velocity gradient would be the slope of this. In other words, it would be du over dy. And I can measure that velocity gradient at any point on this velocity distribution, right? Okay, so this gives me the velocity gradient. Now, I want to consider a fluid element right over here and understand how that fluid element is going to be changed when this plate is moving in this direction and this plate is right over here. Let me bring a prop and show you how this moves. All right, this is what I'm going to use to show you how a fluid element is going to be affected by different velocities. So if I have this fluid element and this is going to be right over here, the velocity on top of this fluid element is going to be higher than the velocity right at the bottom right over here, right? So this is going to create a shear stress, and the top layer is going to move to this direction a little bit. So it will be something like this, okay? So if I want to draw this, this is the element that I showed you, the fluid element. It will look like this. and this is the shear stress on top and the bottom, right? It is very similar to the friction between two solids that are moving on top of each other, right? Okay, so this term, I'm going to represent it by the Greek letter tau, and this is our shear stress. All right, so there is a relationship between this, which is the velocity gradient, and shear stress. So if I want to show that relationship to you, I can graph it. My x-axis would be velocity gradient, du over dy, and my y-axis is tau, or shear stress. For most fluids, this relationship is linear, like this. And the slope of this line is Greek letter mu, and this mu is called viscosity or dynamic viscosity. And so this is really interesting. Now I have the shear stress and I have the velocity gradient. The slope of the line is going to be my dynamic viscosity. You might notice that I said for some fluids, this is a linear relationship, right? For some other fluids, it's not linear. So the relationship could be this. Fluids that have a linear relationship between shear stress and velocity gradient. These fluids called Newtonian fluids. And these fluids, you can see that it's nonlinear. So the slope over here is different from the slope right over here, right? Similarly to that, these fluids are called non-Newtonian fluids. So for these type of fluids, for Newtonian fluids, we can write the equation of this line. So this equation y is shear stress. Our slope is mu, or dynamic viscosity, and x over here is du over dy. And this equation is the equation that describes viscosity, and we call this equation Newton's law of viscosity. Now you might ask, are there any different type of viscosity? Why do we call this dynamic viscosity? There is another type of viscosity, and we show that using another Greek letter nu, and nu is equal to mu divided by density of the fluid. And this viscosity is called kinematic viscosity. Okay. Another question that you might have right now is, I told you that if this relationship is linear, we call these types of fluids Newtonian fluids. And if it's nonlinear, we call them non-Newtonian fluids. Can you give us an example? Absolutely. For Newtonian fluids, water is a Newtonian fluid. Air is another Newtonian fluid. For non-Newtonian fluids, a very famous example is the mixture of cornstarch and water. So if you mix water with enough cornstarch, you get a very interesting non-Newtonian fluid. So I'm going to actually insert a video right after this to show you what happens when we mix water and cornstarch and how this non-Newtonian fluid behaves, and then come back over here to talk about viscosity a little bit more.
When you mix cornstarch and water, weird things happen. Swish it gently in a bowl, and the mixture moves like a liquid. Squeeze it, and it starts to feel like paste. Roll it between your hands, and it solidifies into a rubbery ball, until you try to hold that ball in the palm of your hand, and it loses its structure and dribbles away. To many who have played with this material, perhaps as children, its strange behavior is nothing new. But understanding exactly how, why, and when this material will act a certain way has always been rather unpredictable. But now, a team of MIT engineers have developed a mathematical model that can accurately predict this material's behavior under various conditions. A single particle of cornstarch is about 1 to 10 microns wide and about 100 times smaller than a grain of sand. It turns out that particles at such a small scale experience effects that larger particles do not. Because cornstarch particles are so small, they can be influenced by temperature and by electric charges that build up between them, which causes them to slightly repel against each other. So as long as you move slowly, the grains will repel and slide past each other like a fluid. But if you do anything too fast, you'll overcome that repulsion, the particles will touch, there will be friction, and it will act as a solid. The researchers incorporated equations into their model to describe the effects of particle repulsion and the speed at which the material is deformed, to predict whether it would behave as a solid or a liquid under various scenarios. The researchers say the new model can be used to explore how various ultrafine particle solutions, such as cornstarch and water, behave when put to use, as for instance, fillings for potholes or bulletproof vests.
All right, let's take a look at these two conditions. In this condition, the difference between these two situations and conditions is that the velocity distribution over y is linear over here. So when this is linear, this means that velocity gradient du over dy is constant. How about over here? Over here, the gradient, velocity gradient, the slope of this line is not constant, right? It changes from here to here to here to here to here, right? So over here, it's smaller because the changes between the velocity vectors are smaller. Over here, it's larger because the changes between velocity magnitudes are bigger, right? So over here, du over dy is not constant. So the reason that I have this over here, I want to show you how you can write Newton's law of viscosity for this condition and for this condition. This one is pretty easy. So whenever you have a linear velocity distribution, you can write the Newton's law of viscosity like this. So you have your dynamic viscosity mu, and over here, instead of du over dy, you can replace it with capital U, and capital U is the velocity of the plate on top. And in the denominator is going to be d, and d is the distance between the plate on top and the surface at the bottom. So this would be d. Perfect. This is a simplified version of Newton's law of viscosity. Now, how about here? So we know that du over dy is not constant anymore, right? So over here, you are going to use the equation that I showed you in the a couple of minutes ago. All right. So du over dy needs to be calculated at the location where the value of tau or shear stress is desired. So this du over dy for each point over here is going to take a different value. So this is the difference between Newton's law of viscosity when you have a linear velocity distribution and when you have a nonlinear velocity distribution. Now let's talk about how we can find the units and how we can find dimensions of mu over here, or dynamic viscosity. Okay, so I'm going to actually move everything to the other side of the equation. I'm going to write mu is equal to tau d divided by u. Okay, so whenever you want to find the dimensions, as I talked about in the previous video, and if you don't know, if you haven't seen that, I highly recommend you watch the previous video before watching this video. I'm going to find the dimensions of dynamic viscosity and dimensions of the right-hand side of this equation. Okay, so starting from dimensions of tau or shear stress. Stress in general, so shear stress is tangential force divided by area. Okay, I'm not going to write the dimensions in primary dimensions. I'm going to write them in secondary dimensions. So dimensions of the force would be capital F. What would be dimension for area? So we know that area has the units of squared meters or squared feet, right? So the dimension for that would be L, or length to the power 2. So this is L to the power 2. Okay, so the dimension of shear stress is going to be force divided by area. In other words, it's going to be F divided by L to the power 2. Now, how about the dimension of D? D is length, this distance, right? So it would be L, and also the dimensions for U. U is the velocity, and velocity is defined in physics, distance divided by time. So L divided by T. Now, considering all of this, I can say that dimension of mu is equal to tau is F L to the power 2 times D is L, and over here I have L divided by T. Okay, so this L will be canceled with this one, and what we are going to have is F times T divided by L2. Okay, so this is the dimension of dynamic viscosity, right? Now, if I ask you what are the units for that, you're going to find the units in SI, in the International System of Units. You are going to tell me, so I'm going to write the units in SI. You're going to tell me that the units of force in SI is Newton, the units of time is second, and the units of length is meters and squared. So this is the units of dynamic viscosity. Now, another thing that I know is that Newton divided by squared meter is called Pascal. So I can also write this as Pascal second. This is the standard SI unit for dynamic viscosity. In some textbook and online, you will see that there is another unit that is popular for dynamic viscosity, and that's called poise. P for short. Okay, poise is another unit that we use for dynamic viscosity. It's very common to write the units in centipoise instead of poise itself. Why is it very common? Because if you write the unit in centipoise, the viscosity, the dynamic viscosity of water at room temperature is going to be equal to 1 centipoise. That's why centipoise is very common, so you can compare that pretty easily. All right, so this is how we derive dimensions and the units for dynamic viscosity. You can do the same thing for kinematic viscosity as well. For kinematic viscosity, the units that we have in SI is usually meters squared divided by second. I am not going to derive it for you over here. I will let you derive the units and dimensions for that. And the last thing that I want to talk about is the relationship between viscosity and temperature. This relationship is different for liquids and gases, and we're going to talk about them. Let's start with liquids, and we're going to consider honey. If you warm up a little bit of honey, cold honey, is it easier to flow? Would that be easier to pour that honey? It would be, right? So this is telling you that when the temperature increases for a liquid such as honey, then the viscosity is going to be decreased. So if I want to show that in a graph, this is dynamic viscosity mu, and this would be temperature. Okay, so for liquids, as temperature increases, goes higher, dynamic viscosity is going to decrease like this. And for gases, so this would be for liquids. How about for gases though? For gases, it's a little bit different because as you increase the temperature, the random motion between molecules is going to be higher, and that creates more molecular attraction. And more molecular attraction means more viscosity. So for gases, as you increase the temperature, the viscosity is also going to be increased. All right, and this is the relationship between viscosity and temperature. Now let's talk about one example to make things crystal clear. All right, let's take a look at this example. So this example, again, we have a fluid right in between a plate and a stationary surface that is not moving. We want to figure out what should be the force to create this motion in the fluid. So we don't have the value of the force that creates the motion. Look at the velocity distribution. It's not linear, right? And we have the equation for the velocity distribution over y over here. We know that the distance between, or the gap between the plate and the surface is 4 millimeters. We do have the area of this plate. So this plate is 3D, right? Right now we see the cross section of it, but the area, the surface area of this plate is given to us. And also we do have the value of dynamic viscosity of this fluid in between the plate and the surface. Okay, so we want to find the value of F, or force. So this is a tangential force, and tangential force can be related to shear stress. We know that the equation for shear stress is force divided by surface area. We do have the value of surface area. So if we can find the value of shear stress, then we can find the value of force using this. Okay, what equation can give us the value of shear stress? That's the Newton's law of viscosity. So I'm going to write that. Newton's law of viscosity tells us that shear stress is a function of mu, or dynamic viscosity, times du over dy, or velocity gradients. All right, we do have the value of mu over here. We need to find the value of velocity gradient. Because this is not linear, we need to figure out at what points we want to find the shear stress. We want to find the shear stress right below this surface, right? So we can find the value of force based on that. Perfect. So at this point, our y is equal to what? 4 millimeters, right? Because y is measured from the bottom surface up. Okay, so this is 4 millimeters. All right. Now, how about du over dy? This is telling us that I need to take the derivative out of this equation to find du over dy. So, and it should be pretty easy. So, du over dy, I'm going to take the derivative of that equation in terms of y, 8 minus 0.6y. Okay, now remember that I want to find this gradient when y is equal to what? Equal to 4 millimeters. And notice that the units for y and u is millimeters and millimeters per second. So I can directly put that into this equation. It would be 8 minus 0.6, 0.6 times 4. And this gives me the value of 5.6. Perfect. So this is du over dy. Now I can calculate shear stress. And the result would be perfect. Okay, so this is shear stress. Now the last step is going to be finding the value of force. Notice that the unit is millimeters squared. However, the unit over here, the unit for this number is Newton divided by meters squared. So I need to convert the millimeters to meters, writing the conversion factor. I know that 1,000 millimeters is equal to 1 meter, and I need to multiply it by, I need to have the power of 2 over here. So eventually, the result that I would get for F is going to be equal to Newton. All right, and this is the application of Newton's law of viscosity to find the force required to create this motion in this fluid in between the two plates. All right. Subscribe to the channel to watch more videos about fluid mechanics and learn more about fluid properties and other fluid mechanics topics.